Hello, good day and good afternoon everybody. Today we are continuing with our class GLY3732, and today we are continuing, or I will just give you today and in the next class a small introduction in metamorphic petrology. Yes, in the last 2 hours I gave you the introduction in igneous petrology. Now we are doing the introduction into metamorphism, and after these two introductions we will continue with a more detailed class in regarding to igneous and metamorphic petrology. So when we are talking about metamorphism, then we are talking about a modification of the rocks, and this modification of rocks is caused by changes of temperature and pressure. And these temperature and pressure conditions, they are changing with plate tectonic movements or with the release from large magmatic bodies, etc. So here we have now a nice picture from a strongly folded gneiss. And if you have such strongly folded rocks, then we are talking about metamorphic rocks. I mean, this deformation structure was caused by tectonic movement. So, and therefore we can define metamorphism as a result of alteration of rocks by temperature and pressure. Now something general aspects about metamorphism. So as I told you before, we have changes in heat and pressure and the chemical environment of rocks that can alter mineral composition and crystalline textures, and as a result we are making them then metamorphic. So, and such metamorphic changes occur in the solid, so there is no melting. So that is now a very general, but when we are going then later on more detailed into metamorphism, then you can see, or then you will, I will tell you as well that we have also melting processes when we are talking about high-grade metamorphic rocks, like the formation of migmatites, and that you can see here in Namibia. Then we have here again just such a lecture outline. So, and therefore we will talk about causes, what causes metamorphism. Then the second aspect, we will talk about the different types of metamorphism. Number 3, we will talk about metamorphic textures. Number 4, we will talk about regional metamorphism and the metamorphic grade. Number 5, we will talk about metamorphism and how it is related to plate tectonics. And therefore we will now start with number 1, what causes metamorphism. So we have at first, we have the internal heat from the earth. Yeah, you know that we can subdivide, we have external heat, which we can see here at the surface of the earth. Then the external heat is caused by the sun. And then we have the internal heat of the earth, and the internal heat of the earth is caused by melting processes and by radioactivity. And the melting processes are caused then by plate movements. Then we have the internal pressure of the Earth. Yeah, you know by now. If we are going more into depth, then the pressure conditions are increasing. We have the fluid composition inside the Earth. That is also a very important aspect. That is the fluid. So when the most common fluid, that is just H2O, yeah, that is water, in under hypercritical composition. So and then you have also CO2 inside this fluid, or in most of the cases the fluid is a mixture between water and CO2. So then you have also some methane, and then you can have also some nitrogen, and. So that is a mixture of the fluid. So, but mainly this fluid consists of water. So the next important aspect is that the temperature will increase with depth. And the rate is or varies between 20 degrees and 60 degrees Celsius per kilometer. So we can then expect at the depth of about 15 kilometers, we can have a temperature of 450 degrees Celsius, but we can also have higher temperatures, yeah, because the rate varies between 20 and 60 degrees Celsius per kilometer. So here we have now a nice cross section. That is just a picture, a schematical picture through the upper mantle and the crust. Yeah. So here, for example, very at the rim, we have here the subduction of an oceanic lithosphere beneath a continental lithosphere. Yeah. And here we have the example, here image from North America, yes, and here you have, for example, on the west coast of US, you are North America, the whole continent, you have the subduction of the oceanic lithosphere beneath the continental lithosphere. And here we have then the continental lithosphere. And the continental lithosphere consists of the continental crust, and it is underlined by the mantle lithosphere. So then you have here, for example, while we are, or here where we are facing the subduction of an oceanic lithosphere, you know by now at a certain depth we are producing melt, and the melt production is caused by the rise of water, or the breakdown of hydrous minerals, and that will then cause the formation of melt. This melt will rise up due to the density contrast, and at the Earth's surface we have then the formation of volcanic changes or of a volcano itself. So if the melt reaches then the Earth's surface, yeah, then we are producing extrusivas, such melt which becomes stuck inside the crust will then result in the formation of a pluton or a batholith, yeah. And there we have then a coarse-grained igneous rock, and otherwise when the melt erupts at the Earth's surface, then we have the formation of very fine-grained igneous rocks. So that means we have here also then a metamorphism will occur. That is here just where we have the collision between the oceanic lithosphere and the continental lithosphere, yes. So and then at these areas where the hot melt is affecting the surrounding country rocks, there we will have the formation of contact metamorphic rocks. So then we are going more inside the country, then we have here mountain belts, yeah. So and in these mountain belts we can find strongly deformed high-grade metamorphic rocks. So, and they are characterized by medium pressure and medium temperature conditions, whereas where we have the subduction of an oceanic lithosphere beneath a continent, we will face high pressure and relatively low temperature conditions. Yeah. So, and the pressure and the temperature increases with depth in all the regions here. So therefore we have now here this kind of metamorphic facies diagram, and this metamorphic facies diagram is a little bit different from those metamorphic facies diagrams which I showed you last semester. Yeah, last semester I showed you the metamorphic facies diagram from Escolar 1950, where we have on the x-axis the temperature and on the y-axis the pressure, as well as it is here also. But in that metamorphic facies diagram which I showed you last semester, and this one I'm preferring all the time, the pressure starts at the bottom with 0 kilobar and increases then to the top on the y-axis, and here it is vice versa. Yeah. So you can use this metamorphic facies diagram or the other one. I prefer the other one which I showed you last semester, where the pressure conditions are increasing from the bottom to the top of the diagram. So here these authors made it like this, that it decreases from the bottom to the top of the diagram, because they are arguing when we are walking around on the lithosphere, then the pressure conditions increasing from the top of the lithosphere towards to the bottom. Yeah, therefore they are using this one. So, but anyway, at low temperature and pressure conditions, we are forming then low-grade metamorphic rocks. You know this by now. So, and if you are facing high temperature and high pressure conditions, then we are forming high-grade metamorphic rocks, as it is seen here on the right side of the diagram. So here in this white area at this one here, at very low temperature conditions and at very low temperature conditions and pressure conditions ranging between 2 and 12 kilobar, there we will not form any metamorphic rocks under naturally conditions. So, and here on the y-axis on the right side we have then the depth relationship, and you know by now that 1 kilometer one kilobar corresponds to roughly 3 kilometers. So let us just continue with the next slide. So, causes of metamorphism. So what is the role of the temperature? Yeah. So the role of the temperature will result in the geothermal gradient, and the geothermal gradient is something very important to understand. For example, here in Namibia, it is now of major importance that we are understanding all the geothermal gradients in the crust, because if we are dealing with a high geothermal gradient, then we can use this, for example, to produce energy. So we are talking about a shallow geothermal gradient when we are dealing about 20 degrees Celsius per kilometer. That is not too much. And we are talking about a steep geothermal gradient if we are dealing with a temperature of about 50 degrees Celsius per kilometer. Yeah. So then when we just discussed the role of the temperature, and of course when we are talking about the role of the temperature, then we have also to discuss the role of the best friend of the temperature, and that is then the pressure. So that means, what is the role of the pressure, which we can also define as the stress. We can deal with confining pressure conditions. We can deal with directed pressure. And while we are talking about the pressure conditions, then we have to discuss also what is the rate of the pressure conditions related to the depth, and that is about 0.3 to 0.5 kilobar per kilometer. So that means it is we are facing at a pressure of about 1 kilobar. A pressure of about 1 kilobar is related to a depth of about 3 kilometers. So, and then we can extract from our rock, or if you are going to the field like we have done it last semester, yeah, then you found there at the GLY mountain lodge, you found different metamorphic rocks. Yeah, we had there this mineral paragenesis consisting of garnet, sillimanite, biotite, cordierite. And these minerals have all a certain mineral chemical composition, and they are forming at different pressure and temperature conditions. So, and therefore we can use minerals as geobarometers if we like to get some information about the pressure when they are formed. And we can use other minerals or other exchange vectors as geothermometers, and the combination of both is then called the geothermobarometers. So then we have here again some short questions for this chapter. So the first one is, at what depths in the earth do metamorphic rocks form? What happens if temperatures getting too high? So you should know this already from last semester, where we scratched the metamorphism a little bit. Or you are just using the diagrams from this PowerPoint. Why are there no metamorphic rocks formed under natural conditions of very low pressure and temperatures, as shown in figure 6.1? You should also be able to answer these questions using your knowledge from last semester and this PowerPoint here, and the things what I'm telling you right now. So then we are coming to to chapter here number 2, within the introduction of metamorphism, the role of the fluids. So I mean the role of the fluids, that it has a major impact when we are talking about metamorphic rocks, because without fluids, metamorphic reaction will not take place. So that means the minerals will then just remain as they are, and they will exist under metastable conditions. Yeah. So without fluid, no diffusion processes can take place, and if no diffusion processes can take place, that means metamorphic reactions will not take place. So, and that will lead then to metasomatism, and metasomatism is strongly controlled by the fluid, and therein by the composition of the fluid. So, and then we have that will accelerate it, or that will lead in an acceleration of the chemical reaction. So that is very strongly controlled by the fluid, and also if you have the fluid in excess or not, and then it is also strongly controlled about the fluid composition. That means if the fluid is very water rich, or if the fluid is more CO2 rich. So here we have now another very nice picture which shows us the types of metamorphism. Yeah. So here at the top we have again the continental crust on the left side and the right side. So in this continental crust is underlined by the continental mantle lithosphere. So in between the two continental crustal shields we have the oceanic crust, and in the middle of the oceanic crust we have the spreading center. So, and then we have the subduction of the oceanic plate on the right side as well as on the left side. So, and one subducting plate is shows a steep subduction, whereas the other one is a flat subduction here. Yeah, here we are talking about a flat subduction, whereas here we are talking about a steep subduction. So that means when we are talking about a steep subduction, then we have here a mantle wedge, a hot mantle wedge. If we have here a flat subduction, then the mantle wedge is much smaller, or the mantle wedge even does not exist. So, and everywhere where we have the collision of plates, yeah, for example, caused by subduction, or by the collision of two continents, deformation will take place, and therefore we are forming regional metamorphic rocks. So at the middle ocean ridges you have the production of new material. The one plate is forced to move to the left, and the other one is forced to move to the right. Yeah. There you have the ocean metamorphism also at the ocean floor. So, and here the next thing we have here the impact. Yeah. Here we have a meteorite, and then we are talking about impact metamorphism. Yeah. So, and here it's already written here that here the author called this shock metamorphism. Yeah. And if you are getting such a meteorite on your head, then it can be quite painful. So here we are talking then about regional metamorphism. Yeah. That means we have the collision here, and that will result in the formation of strongly deformed metamorphic rocks, and this can be really high-grade metamorphic rocks. So then we have here high pressure metamorphism. that we are facing in such geotectonic setting where we are dealing with a steep subduction of an oceanic lithosphere beneath a continental lithosphere. So then here we have the rise up of melt. So when this melt will then just accumulate through the Earth's crust, and everywhere in these areas where we have the contact from this hot melt with the surrounding country rocks, we will form contact metamorphic rocks, and therefore we are talking about contact metamorphism. So, and here we have then the last one, which we are calling burial metamorphism. And burial metamorphism is then mostly caused by sediments, and through the sedimentation and cementation, you are forming then, or we are talking then about burial metamorphism. And as I told you before, here close to the middle ocean ridges, we have then seafloor metamorphism. Then again, some short questions for this chapter. You should draw a sketch map and show me how seafloor metamorphism might take place. So then we have now we are talking now about metamorphic textures. So we have here a very nice outcrop, yeah, and in this outcrop we can observe how the directed pressure causes a sedimentary rock, such as a shale, to form cleavage planes that may differ from their bedding planes, yeah. So, and I mean, here you have the outcrop, and on the right hand of this photograph, the author made a sketch map. Therefore, it is always very important that you have a field book when you are in the field, and that you are drawing very, very nice sketch maps with a sharpened pencil. So, and therefore you can then draw very detailed what you can see in your outcrop. And here you can then see the slaty cleavage planes, yeah. They are here, and these cleavage planes, they are caused by the directed pressure on this sedimentary rock. So, and here more horizontally you have then the originally bedding planes. Yes, here are the bedding planes, and here are the cleavage planes, and the cleavage planes are those ones caused by the directed pressure on this sedimentary unit. So, and here we have it again. So here we have a rock unit, and this rock unit of shales and sandstone layers, they are forced by compression from the left and from the right side, yeah. So, and you can see all the originally sandstone layers and the originally bedding layers, yeah. So, and here the author has and we have now here the foliation planes here at the top. So, in the number 2, the author has written the original bedding in a sample of shales of shale is marked by the thin sandstone layer, yeah? And that you can see here, that is this brownish sandstone layer. So, and the regionally metamorphosed rock show foliation caused by the compressive force. So I mean, if we are talking about compressive forces, then we are talking about regionally metamorphic, about a regional metamorphic event, because you need something which can produce the compressive forces. So, and that is what you can observe in the outcrop. So, but now you would like to know how this can be seen, or if there are also some fingerprints of this in thin section. And yes, indeed it is, because the minerals under the microscope, they show then that they are in a foliation. So in the order here under number 4, he has written rocks develop foliation when they contain platy minerals that align along a preferred orientation. Depending on their preferred orientation, compressive forces cause the mineral crystals in the rock to grow or to align perpendicular to the compressive forces, yeah? So I mean, the quartz will then not become aligned, but for example the micas, yes, that is this bluish pink mineral, they are in the foliation, and here the staurolite crystals above as well. So here we have now the same picture again from the investigated thin section. You can see that the staurolite crystal, which is here in yellow, and the micas here, they are in the foliation. So, and that we can see because the foliated rocks contain platy minerals that are aligned along a preferred orientation. So here again we have the same slide, just in a nice hand-drawn picture. Yeah, we have here the compressive forces from left and the right. So, and then we have our mica crystals inside. These are the bluish crystals. They are all in the foliation. Yeah, that is this one. They are this bluish violet crystals. That is all mica, and they are in the foliation, as well as the staurolite. The staurolite here are seen, or the order has made them in yellow. So, and this foliation is caused by a directed compressive force. And as it is written here, foliation is the result of a compressive force. And the mineral crystals become elongated perpendicular to the compressive force. So, and therefore we are talking then about the preferred orientation of a crystal. So we can have a slaty cleavage, we can have a foliation, yeah, like it is shown here in this block or in this hand specimen. We have here again the shale, that is the grayish material, and we have the sandstone layers between. So, and therefore the original bedding can be seen in the thin sandy layers. Yeah, that is the original bedding. So, and then more or less perpendicular to the original bedding, we have then the foliation plane, and the foliation was then caused by the compressive force. So, and that means regional metamorphism causes the cleavage planes to develop. So here we have then a very nice diagram which shows us the intensity of metamorphism increases, so does crystal size and coarseness of foliation occurs. So we have here on this arrow from left to the right, we have increasing intensity of metamorphism. So we have on the left hand low grade metamorphic rocks. Then we are talking about intermediate metamorphic rocks, and then finally about high grade metamorphic rocks. So for example, a low grade metamorphic rock here is a slate, yeah? So, and while we are increasing the pressure and the temperature, the slate becomes then more and more metamorphosed, and we produce a phyllite. So, and if we are going back to our last year class, I told you that during prograde metamorphism, dehydration reactions will take place. So, and therefore our slate here on the left hand will have more bounded water than the phyllite, yeah, because during increasing metamorphic conditions, the dehydration reaction will take place. So then we are increasing the metamorphic conditions again and making from our phyllite and schist. And in the schist we have then already abundant platy minerals, yeah. That means these minerals are in a foliation and we are producing a schistosity. So then again, while we are increasing the metamorphic conditions, we are making from our schist the gneiss. There we have then fewer platy minerals inside. And finally, under high grade metamorphic conditions, this gneiss will start to melt and we are forming then a migmatite. So, and when we are starting from the slate and going to a migmatite, then we will increase the crystal size. And we can also observe an increasing coarseness of the foliation. Yeah, we have in our slate, we have a slaty cleavage. The phyllite still shows a slaty cleavage, whereas in the schist we can observe a schistosity. In the gneiss we can observe the banding, and in the migmatite we have banding, or we can observe banding as well. So now when we are talking about the slate with the slaty cleavage, we are talking about diagenesis, yeah? So, and then we are increasing our metamorphic conditions when we are while we are making from our slate a phyllite, and then we are talking about low-grade metamorphic conditions. And again, our phyllite becomes then metamorphosed to a schist, and such a schist is then formed under intermediate metamorphic conditions. So, and then we are forming finally a high-grade metamorphic rock. So, in the high-grade metamorphic rock, that is the gneiss, or finally, or here in this case, a migmatite. Can also be a granulite, yeah? So, and these foliated rocks are classified by the degree of cleavage, schistosity, and banding. Now we are coming to our next aspect of metamorphic textures. So we have the classification of foliated rocks. So, and that we have, or we are classifying them using then a certain metamorphic grade to describe them. So, and we can classify them also by using the crystal size, the type of foliation, the band and the banding. So, and therefore we have a nomenclature of foliated rocks. We have a slate, we have a phyllite, we have a schist, we have a gneiss, and we can have a migmatite. So, and here we have also something nice. We have here a schist, yeah. And you can see very nicely the schist with the schistosity here. And we have, this schist contains garnet porphyroblast. So here the author forgot an Y. It should be not a porphyroblast, it's a porphyroblast, yeah. So in such a porphyroblast, that is garnet can form a porphyroblast because they are round. So when porphyroblasts are always formed by minerals which does not show any orientation, and the garnet cannot show any orientation because it's more or less round, yeah. So we can then also call them granoblast, yeah. So when we are talking about a sillimanite needle, for example, then it is not a granoblast or a porphyroblast, because sillimanite is a needle, and it does not matter how the sillimanite needle is inside the rock, it shows always the orientation, yeah. So here we have it already, nomenclature of granoblastic non-foliated metamorphic rocks, yeah. So such a granoblastic metamorphic rock, that is for example a granulite. In a granulite you cannot observe any foliation anymore. Or the hornfels, and hornfels is a conduct metamorphic rock. So when the hornfels was not affected by high directed pressure conditions, the hornfels was just heated up. Then a quartzite is also a granoblastic rock. Marbles, greenstones, amphibolites, and granulites, yeah. So in the granulite case can also be called the granophytes, yeah. So these are then the granoblastic rocks. So here this quartzite, for example, has a granuloplastic texture. There are a lot of quartz crystals inside, and these quartz crystals do not show any orientation, yeah? Here we have now table 6.1, deals about the classification of metamorphic rocks by the texture. So we have the classification, we can deal with a foliated rock, or we can deal with a granuloplastic non-foliated rock, or we can deal with a porphyroblastic rock. So we have here now the characteristics. When we are talking about a foliated rock, then we are talking about a distinguished, and it is then distinguished by the slaty cleavage, schistosity or gneissic foliation. Mineral grains show preferred orientation, yeah? Whereas the granuloplastic rock has as characteristics granular, characterized by coarse or fine-grained interlocking grains, little or no preferred orientation. So and the porphyroblastic rock shows large crystals which are set in a fine-grained matrix. Now we are looking for the rock names. So when we are talking about foliated rocks, then we are talking about slate, phylites, schists and gneisses. When we are talking about granuloplastic rocks, then we are talking about hornfelds, quartzites, marble, argillites, greenstones, amphibolites and granulites. And such porphyroblasts can occur in slates up to gneisses. So last not least, we have now the typical parental rock, yeah, the typical parent rock, that means the precursor of this metamorphic rock. So when we are talking about slates, phylites, schists and gneisses, we have as a typical parental precursor a shale or a sandstone. So when we are talking about granuloplastic rocks, then we are having as a typical parental rock a shale or a volcanic rock for producing or which can produce later on an hornfels. Then the quartzite has as a parental rock a quartz-rich sandstone. The marble has as a parental rock a limestone or a dolomite. The argillite has as a parental rock a shale. The greenstone a basalt or a shale. The amphibolite a shale or a basalt. And the granulite also a shale or a basalt, yeah? So, but we have here at some of the granuloplastic rocks like the greenstone, the amphibolite, the granulite, they have here a basalt as the parental rock. I mean, that can then be, of course, also a gabbro, yeah? So these are just a few examples. So and then for the slate to gneiss, we need a shale as a typical parental rock. So, and that was it for today, and tomorrow I will then upload the next or the second part of our introduction into metamorphic rocks.